Hello students, I am myself V. Nair from Department of Physics, CMD PGA College, Bilaspur. Today I will be going to deliver a lecture on the topic electromagnetic energy and the associated concept of Poynting's theorem and Poynting's vector. The objective of the lecture is to derive a statement of the energy conservation law using the Maxwell equation to express the conservation law in a form which is similar to the continuity equation, identify the flow of rate of flow of electromagnetic energy per unit area as the Poynting's vector, and finally to show that the Maxwell equations are consistent with the more general principle of the conservation law of energy. Few things we will have to recall. One of that is we have studied that the energy contained in an electromagnetic field is the sum of the electrostatic energy and the magnetostatic energy, and that energy can change in a closed volume. So first of all, let us discuss the energy associated with a collection of charges. For example, if we are charging a capacitor, then there will be an accumulation of charges, and the work done in accumulating these charges will be stored in the form of potential energy. Such an energy of an electrostatic field in a capacitor is distributed in space and is given by We equal to epsilon 0 by 2 volume integral of E square dV. We have assumed that no dielectric material is present here. And from the equation above equation, we can find out the corresponding energy density, which is UE equal to half epsilon 0 E square. This energy density is the energy per unit volume, and this expression is true for a linear medium. Similar to the capacitor, an inductor has also the capacity to store energy in its magnetic field, and that energy is a manifestation of the work done in carrying currents against the back EMF. The corresponding expression for the magnetostatic energy is 1 upon 2 mu 0 volume integral of B square dV, and the corresponding magnetic energy density will be given by the expression B square by 2 mu 0. Again, this expression is true for a linear medium. Now, if both the electric field and the magnetic fields are present, then the total energy stored in the fields is given by We dash B equal to half volume integral of epsilon 0 E square plus B square by mu 0 into the elementary volume dV. And the corresponding total energy density in that electromagnetic field will be given by half the integrand in the above integral, which is half epsilon 0 E square plus B square by 2 mu 0. Now let us understand that how this electromagnetic energy contained in a particular volume can change, or how does the transport of such an electromagnetic energy take place. For this, let us take the example of energy flow in a simple DC circuit consisting of an ordinary flashlight. Now, the electromagnetic energy flows from the battery to the bulb, where it is converted into heat and light. It is important to assess whether the energy flows through the conductor like the flow of water in a pipe, or in the surrounding of the conductor. It is surprising to note that the energy density in the conductor is much small to account for the amount of energy, total energy in the transit process. Nearly all of the energy that gets to the bulb is flowing through the space surrounding the conductor. So essentially the conductor is a medium which guides the energy, but it does not carry much of the energy. One important point I will here highlight is to describe any flow of energy through space, it is useful to use the term the power radiated or the power crossing per unit area perpendicular to the flow. So one of the important factors in the flow of energy, electromagnetic energy, is the power radiated per unit area. That area should be perpendicular to the direction of the flow of electromagnetic energy. Now coming to the Poynting's theorem, we have to establish the statement and the mathematical form, which includes both the integral and the divergence form, differential form. So let us separate a region of space which is consisting of a number of charges, circuits, batteries, resistors, etc., where a microscopic electromagnetic field exists. Thus, this separated region of space has a volume V confined by a closed surface F, and the total electromagnetic energy in this volume V is given by WEB, volume integral of UEB dV. Remember, this is our equation number 1. So, for discussing or establishing the Poynting's theorem, we first of all start with a particular volume in which the electromagnetic field energy is given by the expression 1. Now, how does this energy contained in this field change? There may be two ways by which the energy can change. The first is by the mechanical work done by the electromagnetic field on the currents which would appear just as the Joule heat. The second is by the radiative flow of energy across the surface bounding the volume. Now let us introduce the vector S representing the energy flux density, that is the total amount of energy which is flowing per unit area per second. So energy flux density S is a very important vector. We should be able to distinguish it from the power radiated per unit area. So power radiated per unit area and the Poynting's vector and the vector S, which we will later call it as the Poynting's vector, are different quantities. Now if we know the energy flux density, we can calculate the total flux of energy flowing through the outward surface F per unit time, which is written as just this normal component of the uh, vector S over a closed surface F, which by Gauss divergence theorem is equal to divergence of S dV over a volume V. This electromagnetic energy contained in the volume V can transform into other kinds of energy. For example, it can do work on the charged particles contained in the volume V, and we can calculate the rate of work done on these charged particles contained in the volume V, which is given by d upon dt of W mechanical. The energy WEB thus contained in the volume V may diminish because of, one, the energy flowing outwards through the surface F, and secondly because of the work being done on the charged particles of the substance. Hence we can in the initial stage we must establish a relation which is of the following form, with minus d by dt WEB, which is the rate of decrease of the electromagnetic field energy, and that decrease is equal to some amount of energy which is being flown outwards the surface F, given by integral of S dot n dA, plus a amount of energy which is being expended in doing work on the charged particles of the substance. Equation 3 can thus be written as dW by dt equal to minus d by dt WEB minus surface integral of F S dot n dA, or d upon dt of WEB, we know it is the volume integral of the energy density over the volume V, and surface integral of S dot n dA can be converted into a volume integral again over the same volume V as volume integral of divergence of S dV. The energy density UEB and the energy flux density S are functions of quantities characterizing the original E and B fields. We need to form the explicit form of these functions U and S. Let us attempt first to transform the expression for the rate of mechanical work done on the charged particles. So we will be calculating dW by dt, where W is the mechanical work done. And then we will split it into two terms. One of the terms will be the time derivative of a scalar quantity, which we would be able to identify with the energy density of the electromagnetic field, and the other addend of the will be the divergence of a vector quantity, which we would be able to identify with the vector S. Now let us calculate the work done per unit time by the field forces on the charged particles. The Lorentz force on a charged particle moving with a instantaneous velocity v is given by q into E plus v cross b. During an infinitesimal displacement dl, the work done will be equal to dw equal to q into v cross b dot dl plus q into E dot dl. And the rate of mechanical work done will be on a single charge particle will be q into v cross b dot v plus q into E dot dl by dt, which is v. And v cross b dot v is 0, which is accordance with the fact that the work done by the magnetic force is 0. So dW by dt, or the mechanical work done, rate of mechanical work done on the charged particle, is q into E dot v. If only one species of charged particles are present, then if we have to calculate the total rate of mechanical work done on the charged particles contained in a volume V, then first of all we will have to replace Q by rho dV, where rho is the charge density, and then integrate it over the entire volume. So d upon dt W mechanical is volume integral of rho dV into E dot V, and if we arrange the terms, we get rho into V dot E into dV, and rho into V is the current density expression. So dW by dt mechanical is volume integral of J dot E dV. Now in this expression 8, we have to replace J, and this can be done by using the Ampere-Maxwell law to eliminate J. Curl of B is mu 0 into J plus epsilon 0 into del E by del T, or curl of B is equal to mu 0 into J plus epsilon 0 into E is D. So this comes out to be del D upon del T, and if we take mu 0 on the left side, we get curl of H equal to J plus del D, and taking J on one side, J equal to curl of H minus del D by del T. Now using equation 9 in equation 8, we get E dot J as E dot curl of H minus, in the parenthesis, minus del D by del T into the elementary volume dV, or E dot J dV becomes equal to E dot curl of H minus E dot del D by del T dV. Now look at this first term on the right hand side. We need to convert it in a form so that we can use another Maxwell equation. For this, we remember the vector identity of divergence of E cross H is just H dot curl of E minus E dot curl of H, or E dot curl of H becomes equal to H dot curl of E minus divergence of E cross H. Now curl of E is, from the Faraday's law, it is minus del B by del T. So E dot curl of H becomes equal to minus H dot del B by del T minus divergence of E cross H, and this is equation number 11. So in the equation number 10, we had a term E dot curl of H, and for E dot curl of H we have the expression 11. So substituting the expression 11 in 10, we get in volume integral of E dot J dV equal to minus volume integral of, in the integrand, minus divergence of E cross H minus E dot del D by del T minus H dot del B by del T. This is equation number 12. We have assumed here that the macroscopic medium involved is homogeneous and isotropic. Homogeneous means the medium has the same macroscopic properties at each point in space and each direction. And the medium has the permittivity epsilon and the permeability mu, which are being considered as constant. Also, the constitutive relationships between D and E and between B and H are assumed to be linear. So, D equal to epsilon E and B equal to mu H. With these considerations, we can interpret the various terms in the equation 12. Let us recall that the total energy density of the electromagnetic field is given by half epsilon E into E square plus B square by mu, and E square can be written as E dot E and B square as B dot B, and epsilon into E gives D, so first term becomes D dot E and the second term becomes H dot B with half outside the bracket. And if we partially differentiate it with respect to time, we get half del D by del T plus dot E plus D dot del E by del T, and again two symmetric terms as these two terms, H dot del B by del T plus del H by del T dot B. So again, these two terms are similar and these two terms are similar. So essentially, it is twice E dot del D by del T plus twice H dot del B by del T, and that 2 gets cancelled and we come out with an expression as E dot del D by del T plus H dot del B by del T. And this is the rate of change of electromagnetic field energy density. Now using equation 13 in 12, we get the rate of change of mechanical work done, which is equal to volume integral of E dot J. This becomes equal to minus volume integral of, in the integrand it is divergence of E cross H over the volume V, and minus del upon del T volume integral of UEB dV. And for E cross H, we substitute a new vector S. So S is E cross H and it is called the Poynting's vector. And for the partial time derivative, we have substituted it by the total time derivative as the volume remains fixed. So we get, if we rearrange the terms, volume integral of E dot J plus divergence of S plus d by dt of UEB. This is in the integrand, and the elementary volume dV equal to 0. This integral is valid for any arbitrary volume, and hence this integral will be 0 only if E dot J plus divergence of S plus d by dt of EB equal to 0, or we get divergence of S plus du by dt. U is the electromagnetic field energy density equal to minus E dot J. So from either from the equation 14 or 15, we can summarize that these equations represent the energy conservation equation in electrodynamics. If we convert the volume integral into surface integral, then containing the Poynting's vector, then we can rewrite it as volume integral of E dot J dV equal to surface integral over the surface F of the Poynting's vector minus d by dt of the volume integral of the energy density of the electromagnetic field. So this is the integral form of the Poynting's theorem, and similarly we can get the differential form of the Poynting's theorem. One final thing we should remember is, what does this Poynting's vector signify? So for the physical significance of the Poynting's vector, we can calculate the units of the Poynting vector. So E has a unit of Newton per Coulomb and H has a unit of Ampere per meter. So Newton upon Coulomb into Ampere. For Ampere we substitute Coulomb upon second into 1 upon meter. Multiply it on the both numerator and denominator by meter. So we get a coulomb gets cancelled out and Newton into meter becomes joule and second into meter square. Now joule per second is the unit of power or the watt. So the unit of the Poynting's vector is watt upon meter square. So Poynting's vector has the unit of the power radiated per unit area. So this is an important quantity. It is not just the power, but it is the power radiated per unit area. So this was the lecture for the present time, and hopefully we will be able to interact in our next lecture. Thank you.